Have you ever just looked at one of those massive cruise ships? I mean, they're basically floating cities made of steel, and just thought, how? How in the world does all that metal not just sink straight to the bottom of the ocean? Well, the answer is this really elegant piece of physics that was figured out more than 2,000 years ago. And that really is the big question, isn't it? You take a tiny little steel nail, drop it in a glass of water, and it plummets right to the bottom, no hesitation. Yet, you've got a colossal aircraft carrier that weighs hundreds of thousands of tons, and it just bobs around on the surface like it's nothing. So what's the secret here? It's not magic, I promise. It all comes down to a legendary eureka moment.
And to get to that moment, we have to go way back in time to ancient Greece, to one of the greatest minds of antiquity, a guy named Archimedes. His story is honestly one of the most famous tales in science, and it all kicked off with a king, a suspicious crown, and, yeah, a bathtub.
So here's the setup. The king's got this new crown, but he has a sneaking suspicion the goldsmith cheated him and mixed in some cheaper silver. So he goes to Archimedes and says, "Figure this out for me, but you can't damage the crown." Archimedes was totally stumped until, one day, he steps into his bathtub and watches the water slosh over the sides, and then bam, the light bulb goes on. He realizes the volume of water that spilled out was exactly the same as the volume of his body that went in, and just like that, he had a way to figure out the crown's volume. He'd found it.
And that observation right there, that's the first huge piece of the puzzle. It's called displacement. And the idea is actually pretty simple. When you stick something in water, it has to take up space, right? To do that, it has to push or displace an equal volume of water out of its way.
But here's the thing. What Archimedes stumbled upon was so much bigger than just a clever way to check a king's jewelry. He had accidentally uncovered a fundamental force of nature, one that explains everything from giant battleships to the rubber duck in your tub.
And that force has a name, the buoyant force. The easiest way to think about it is that it's the water pushing back. When you try to shove an object into the water pushes up on it. And that upward push, that's the hero of our story today.
So this brings us to the big one, Archimedes' Principle itself. And the golden rule is this. The strength of that upward push, the buoyant force, is exactly equal to the weight of the fluid that the object pushes aside. And that's the secret sauce right there. It's not the volume of the displaced water that matters, it's the weight of it.
Okay, so if we know the rule, how can we actually tell if something's going to float or sink? Well, it all comes down to a simple fight, a competition between two forces that are always working against each other.
I love this way of thinking about it. It's literally a tug of war. On one end of the rope, you have gravity, constantly pulling the object's own weight down, trying to sink it. And on the other end, you have the buoyant force, pushing up, trying to float it. Whoever pulls harder wins. And the rules of this competition are super simple. If the downward pull from the object's weight is stronger than the water's upward push, it sinks. End of story. But if that upward buoyant force is equal to or even stronger than the object's weight, ta-da, it floats. Okay, but wait a second. This is where things get a little tricky, because it seems to go against what we all learn as kids. You know, heavy things sink, rocks sink, nails sink. So how does our 200,000-ton ship even stand a chance in this fight?
All right, let's just bust this myth right now. The idea that heavy things sink is, well, it's not the whole story. The truth is, floating has nothing to do with how heavy an object is on its own. It's all about the balance of those two forces. And the secret to winning that tug-of-war, the secret to creating a massive upward push, isn't weight, it's shape. A solid block of steel sinks because it doesn't displace much water. But you take that same steel and shape it into a giant hollow bowl, you know, like a ship's hull, and suddenly it can displace a ton of water.
And just like that, that's how a 2,000-year-old idea from a bathtub became the fundamental principle behind some of the most massive things humanity's ever built.
Just to give you a sense of scale here, try to wrap your head around this. A large aircraft carrier has to push more than 100,000 tons of seawater out of the way just to float. That means the ocean is pushing back up on it with a force of 100,000 tons. That's just wild. And once you get this, you start seeing this principle absolutely everywhere. Ships are the obvious one, sure. But submarines? They are masters of buoyancy. They have these things called ballast tanks that they can flood with water to get heavier and sink, or they can blast the water out with air to get lighter and rise to the surface. And get this, hot air balloons do the exact same thing. They're just floating in a different fluid, the air. They float by pushing aside all the cooler, heavier air around them. So we've gone from an ancient Greek bathtub all the way to modern oceans. After all of that, what's the one big idea you should really take away from all this?
It really all boils down to this. It doesn't matter if it's you in a swimming pool, an ice cube in your drink, or a supertanker out on the ocean. The universe is always giving a little upward boost to anything sitting in a fluid. And the size of that boost is always, always equal to the weight of the fluid it had to shove out of the way. That's it. That's the whole secret.
And to finish up, I want to leave you with a classic little physics puzzle to chew on. So picture this. You're in a rowboat on a small, calm lake. You have a really heavy anchor in the boat with you. You decide to throw the anchor overboard, and it sinks to the bottom. So the question is, what happens to the water level of the entire lake? Does it go up, go down, or stay exactly the same? Think about all that water being displaced before you throw it in versus after. The answer might not be what you think.